Right, okay, let's get going. So we are going to talk about the stuff that I just brushed through very quickly last time, namely the models that we're actually going to use, but just begin with a short summary of what I tried to talk about last time. So basically, the whole thing, right, that I tried to convey, there's no magic bullet. Machine learning is not this magic thing that just happens, that we just throw some data at and it does cool stuff without us needing to do anything or know anything, so forth, right? That was the whole message, really, of the main part of the lecture. So machine learning, what it really is, right, the way we should see it, is that it's this glue that allows us to take a very carefully processed, thought through data and the stuff that we know explicitly, or most likely as data science, you don't know this, but there's someone else who knows that. And you can talk to them and you can get something out from that. Our task as if you're a machine learner, the real task is to try and say, can I formulate that stuff mathematically somehow? And then we have lots of churning of compute, and then we can glue these things together to get something more. That's really what machine learning is. So then what I tried to talk about was to say that, you know, there's actually theory around these things. And I just super quickly did what you would do a whole course in, which would be like computational learning theory or something. And I just threw out some stuff. And basically we talked about this framework called pack learning, which was probably approximately correct learning, which is one of the ways to start framing a theory about this. And from that, you can show what people who do pack learning or learning theory are obsessed about is trying to find bounds of this. What are the limits of stuff that we can do? Pretty much two things that I hinted at and gave you some references for looking at those proofs is that we need a lot more data than we think to do most things. And secondly, there's no such thing as this is always good. There's a no free lunch in there. And then when you come to that in practice, so what these people who look at the theoretical side of things shows, we're doing a lot better than we should. We shouldn't be doing this well. Machine learning works much better than it should be doing. So we're doing something else. And a lot of that something else is what we've been trying to communicate in this course, right? So we often think that the data where we start doing machine learning on is just there. It's not. So this data, when we collect it, when we decide to measure stuff, we include an enormous inductive bias in this, right? And that is knowledge in itself, right? And that's the access part. And then the assess part is that when we think about data, when we actually know that, cool, now I have this, we hand it off to someone else, they would do stuff with this data. This is also introducing an enormous amount of biases in this, and good biases. This is the stuff, this is the bread and butter, right? Introducing these things. And then the last part then, which is often then the machine learning part, the address part, I just said because it's kind of funny, if you know Judea Pearl or read this book, the book of why, he has this quote where he says machine learning is just curve fitting, but it's quite exciting what you can do with curve fitting, right? And that, the narrative, and the reason why we argue according to these three words, is the narrative has been placed that it's all in the last point. And I would argue it's not. Right? The last point is really hard to do, and we're trying to make science of it. The first 2 points is where a lot of the work actually happens. But in order then to get this course, to get this holistic thing that I guess we're trying to communicate, we need to do all parts, right? Because these three words are not just sitting isolated and we can just do a course on each. In order to understand everything, because you go back and forth and work in this, we have to do all parts, right? So that's why I'm doing this green part, which is then talking about the address issues. So to do that, we're then going to talk about these generalized linear models. And I'm going to quickly go through the slides that I did last time. So because I knew I did that very quickly. And then we're going to look at these models more in specific. And these are things that are incredibly powerful, and you can do a lot of them with them. And as I said, there's really good code for them. So there's lots of things that we don't have to deal with. We're not going to deal with effectively how you train these models. I'm not going to talk about that pretty much at all. We're just going to assume that that works, because we can assume that it works, because it kind of works really well. Cool. So our setting was this. We have something which I'm going to refer to as an explanatory variable, x, and we have a response variable, y, and our task is always to explain the response from the explanatory variable. That's our task. So we've seen this, done this, tons of us, lots of times by doing linear regression, right? So linear regression, we think about it like this. It's normally, well, this is what linear regression actually is that we say that I take my explanatory variables, I weigh them together using some coefficients, and these are the coefficients that I want to learn, these are the model parameters. And then I say, I have not actually observed the truth if x and y are completely deterministic. I don't observe them because this thing has been corrupted by some additive noise, and this noise itself is Gaussian. Okay, so then when we want to remove this randomness from the data to make a decision, we look at the expected value. So if we take the conditional expectation of saying what would yi be at xi, we take the expectation over this model. So if we take that expectation, just following the rules of expectations, we can break that up into a sum. We now have the expectation of the noise, which is 0. And then we got this. So that means that our linear regression model is just taking this linear predictor, and then we get the expected value at y. Okay? So that's hopefully how you've seen linear regression being explained. So now there's another way of thinking about this, which is more general, And that is to say, cool, I got the same underlying model, but I'm not going to think of the noise as something that's being added to this only. I'm going to generalize this, and I'm going to say that it's going to move the noise over, and then I'm going to encapsulate the noise itself in the response variable. And now what we're going to do is we're going to say that the response variable is random. So the response variable now follows some distribution. And that distribution now we're free to pick, right? So in the Gaussian case, we just said, I just add this noise, okay? Now, if I would look at that in specific, what I now have instead is that I have a response variable, which is distributed as a Gaussian, in this case, around this y, which, well, we don't have anymore. And if I would write up this model, then I would just have it like this. I have a response variable that is distributed with variance and mean like this. Okay? Right. So now the step then of a generalized linear model is to now generalize this concept. So the key things that we're going to have is that how we combine the explanatory variables is always going to be a linear combination. That's where the linear comes from, right? So we always have x times beta in one way or the other, right? Okay, we're going to loosen that a little bit, but the way you're going to see it is you're always going to have a sum over betas. It's linear in beta, right? Doesn't necessarily need to be linear in x, but it's always linear in beta, okay? And then what we're looking at is the first moment, the expectation over the response given the explanatory variable. And now we're going to say that the distribution that yi is allowed to come from comes from this thing called the exponential dispersion family. And then we're going to have a link function, and the link function is the thing that connects the first moment to this linear predictor. Okay? And another way of just looking at that, which might feel more natural, is to think of it as I want to predict the expected value of y at one point. I have a linear model. I take this linear model, I combine it into a scalar value, and I push that through a function. Okay? Now, that, if you've been taught neural networks, that looks an awful lot like an activation function and something else. You want to read an article that talks about this connection. This link here is quite good, where they try to explain deep neural networks as just a recursion of this. That's actually the only thing it is. But this stuff is much older and doesn't use the word deep. So no one really cares so much about it. But well, if you're a statistician and if you want to do sensible work, you care a lot about this. So it looks an awful lot like a neural network if you think about it in that setting. Cool. So why are we doing this? Because another way of thinking about it, this is actually quite a subtle but a really important notion. So stop me in this. So let's say that another way of thinking about this, to say, is that, well, is the only thing I'm doing, why can't I just see it as linear regression, where I just do a transformation of the data, right? So I just do this, right? And then I do a regression on this. If I do regression on this, it's very important that to think of, in this case, this here, the noise is distributed as a Gaussian. And that means y is definitely not going to have Gaussian noise on it. It's going to look something like that over there, because it's actually, now you would have to exponentiate this. If you want to look at the noise, it's actually the exponential of this noise, right? If you just transform the model, you don't get this, the setting that we've explained. You can do this with a general linear model as well, but it's not the Gaussian model. What we're doing is this, right? The explanation that I said. I said that y is Gaussian. I've in this case picked a log function too. And that means that the noise on this, if you want to think about it as noise, this y is Gaussian distributed. So that's something much more like that. So just taking the problem and transforming it and saying, oh, I'm just doing linear regression, normal linear regression over some transform variable is not the same. You see that? Yeah, so that's just very important to remember, because when you do these kind of transformations, you're actually completely changing your assumption about the noise, right? Or the randomness in the system, right? Okay, and when we do generalized linear models, we're always talking about the randomness in the response, right? Here, the randomness in the response is an effect of what we said that randomness to be, right? And that's different. Yeah, cool. So this exponential dispersion family looks like this. That's the canonical representation of this family. I've tried to rewrite most derivations in terms of this. Sometimes it gets very, very messy. But I'll try to do my best. But it basically has two parameters, a location and a scale. And we're always, throughout this, for inference, assuming that the samples, the data has been drawn high ID. So when we want the probability for all data, we just take a product of this distribution, right? Okay. So the Gaussian, if you want to rewrite the Gaussian on this form, it looks like this. I've used identify the parameters, and you've never seen a Gaussian being written like that, but you can kind of see that that would make a Gaussian eventually, the normal way we would write it, right? So the good thing about writing it on that form is that now I know, if I know what this d of theta was the location parameter, then I can always just compute the expected value and the variance using a general formula like this, okay? You're not going to have to do this. We have all this in code, but you can kind of see how nice it would be if someone specifies these parameters that you can use quite nice and general code for these things, okay? Right, so then if we look at the package that we're going to use, it's super simple. So you're going to import Statsmodels, and then there's only one call that you're ever going to need to use, or two calls, three calls. So you create the model, and you create the model where you give the response and the explanatory variables, and then you pick the family, the distribution of the response variable. In this case, I picked it to be Gaussian, and then you pick the link function, just like that. So this here will be a Gaussian model with a log link function. That's it, okay? If you don't give the link function, you would pick what's called a canonical link. And the canonical link is the link that would make the g function map directly to the location variable. So the Gaussian, that will be identity, right? Okay. So the families that you can pick from are these, and some of these you will know. We would look at, in this lecture, we'll look at the binomial, the gamma, the Gaussian you've already seen. We'll look at the Poisson. The Tweedy distribution is a generalization of a set of distributions. I've never ever used it, but it got a very cool name. So then these are the link functions. You're most likely, we're going to use the logit, the log. You can look at these to think about what kind of models you would want to train. And what I'll do now is I'll go through a set of different models and how I think about designing them. Yeah. So then you fit, we're going to look at two commands to fit it. One is this one, which is just an unregularized fit. We're later going to look at regularizer, and then it is fit underscore regularized, and it has some additional parameters. And then what you do predictions like this. The nice thing about Statsmodels is that it works all with pandas, which means that that prediction, as you can probably see, is just a pandas data frame. So all the stuff you've done, this should just fit in really, really well with that, right? It shouldn't be much work. And this is really the only thing you have to do, right? And we don't want, and this is part of the reason why we're working with these models, we want you to think about why you're applying the model, not spend all this time getting a model to work, right? That's the aim, right? And we're going to trust that that fit thing actually does its job, and it does. Yeah, cool. So then let's do the first one then. So all these crazy lines is a binomial distribution. The binomial distribution you would use if you have something which is like a frequency of success, for example. So let's say in this case, I do 4 trials of something, and I want to know the probability that a certain number of trials are successful, right? You can use this for biased coin tosses, for example. So here is a set of binomial distributions. So what I'm predicting in this case is a probability, right? I'm predicting the output is actually a probability. How likely is it that all 4 of the trials succeeded? And now we want to parameterize that distribution using a linear model. So this is what we have. So I got something, in this case, let's just do this in 1D. So I have 2 betas that I need to learn. I have y, which comes from this, I've said this is binomially distributed. So now y is effectively a probability. So I know, or a frequency or a ratio or an odds, if you want it. So now there's 2 things to think about. I need to limit the possible y's to 0, 1, right? Because otherwise it's just, there's no probability that it's more than 1, right? So I need to pick, so one way of thinking about when you design these models is to pick a link function that limits those values. The classical link function that does that is the logit function. So the logit function would take a value y between 0 and 1 and map that to plus minus infinity. Yeah. So you've most likely seen this function. So if I just do churn, do some derivation, just look at the first line and the last line. You've seen this one, right? That's what's called the sigmoid function. This is usually if you do classification in a neural network, this is a function that you'll see. So this is just taking a binomially distributed data with the logit function as a link, you get something which is called logistic regression. And this is a very, very useful thing for doing binary classification, for example. So I found this data set used to show you how of just actually fitting this. So apparently this is someone prodding cows with a certain amount of current to see if they react. And then you increase the current and you see the number of cows that react to this. So you've got current here. You have 70 trials of the cows, and this is the response that you got. And this is then the proportion, which is the variable that we want to. Apparently it was not a lot of current, but this is the proportion that you want. So this here is my response variable, and this here is my explanatory variable, right? And now we just want to set this up. So if I do that, like this is the command. So you pick that data, I pick the family's binomial, and I pick a link function that's logit, I do fit, and then I do predict. That's what I get. Okay? So this is the current, and if you can see, if you go out here and predict way outside where you've been, it's going to flatten out asymptotically to 1, right? And then you can probably try and give it a negative current, and we'll see what happens. Yeah. Okay. So that was the binomial. Super easy, logistic regression, nothing different at all. Okay. So then something which I think would be quite potentially useful for you in this for the task that we've set to is something called Poisson regression. So Poisson regression is if you have a classical example of this, if you've got arrival times. So I have a restaurant, and generally I don't have a restaurant, but if I had a restaurant, and let's say I was really good at cooking, so there would be 500 visitors coming to my restaurant per day. What is the probability of within a specific time interval this many customers arriving, right? Well, there could be a probability that everyone arrives the first hour and so forth. That's Poisson regression. You can do this. Another classic example of this is failures of products. So if I build a car and I know I expect this many to break of this, so I'm thinking insurance, what's the probability of all of them breaking at the same time, right? Okay, how many, what you know, how much do I need to design my facilities for being able to cope with this? Okay, so now we're going to do a different way of thinking about this model, this generalized linear model. So the Poisson distribution, oh, sorry, let me revert. How did we think about the link function in the previous case? I thought about the link function as saying, oh, cool, I know my response is this, it's binomial, and then I needed to have this characteristic. Let's pick a logit function, and then we churned it. Now I'm going to think about it in a slightly different way. So I'm going to write down what the Poisson distribution is, and then I know the expected value of this is lambda. So lambda here is the parameter that should be parameterized by my linear predictor. So counts are somehow positive. So I need a positive link function. It needs to only generate positive values. So I'm going to pick a log link function. So effectively, I'm doing the exponential of the linear predictor. So that means the model I've actually designed, sorry about that, should be up there, is actually this. Okay? So this is the probabilistic model I've now designed. The lambda is the thing that my linear predictor predicts. I picked an exponential form of the linear predictor because I picked log as the link function. That means this is the probabilistic model. Okay. So where effectively what I'm doing is that at each place, depend on x, I'm predicting a different lambda. Right? So I have a different Poisson distribution at every x. So a classic example of this is this type of data. So this is data from the Brooklyn Bridge in New York. So here I have lots of explanatory variables, the dates, the day of the week, the month. I have temperature, I have if it's raining or not, and I have how many cyclists are crossing this bridge, right? So that's a typical example. You can think about this could be house sales, not say more than that, right? So here is just taking the log is the canonical link function for the Poisson. So in this case here, I've just fitted this with this. My blue is the actual data, and the red is the fit of this. Okay. So nothing very strange about that. The last one I'm going to go through, just to see this in a slightly different way again, is a continuous one. So this is gamma regression. So gamma distribution are often used for weighting times, and it has this type of structure, right? So you're often using this for predicting things like where you have a distribution which are skewed, right? So you might have, for example, a mean, and you've got errors that are just propagating in one direction, right? So let's look at a typical example. I'll show you this and then I'll go through the math. So here we would have something like this. If you would fit this with a Gaussian distribution, it would fit it slightly higher up, most likely, right? So you can have something where sometimes it goes really, really wrong, right? So you have this distribution that goes up like this. So in this case, the gamma distribution looks like that. And I have the expected value and the variance being this. And if I write this on, it's the canonical form that we talked about before, it looks like that. So now this is another trick of the trade thing, I guess. So if you would derive the canonical link function for the gamma distribution, so the one that directly relates it to the scale parameter, you would use this, because that's how it would work. If you would connect it to the location parameter, you would use this. But I've never seen anyone use this, and I don't know why that is. Neil might know more than me. Everyone I've ever seen uses gamma distributions with a log. So generally, you would always see the gamma distribution used with a log link function. So that's a distribution that you can use if you got this type of data, which I think you are quite likely to have. Cool. So I could be now like a broken record and just keep going through model after model after model. What you should be doing is that you should be familiar with how these distributions look like. Wikipedia is great because in the top corner of every distribution plot, there is a nice plot of how it looks like. Then what you're going to do is you're going to get the data, right? You have the data, you've been processing data. You're going to look at it and see, oh, how does this data look like? And then you'll see, actually, that looks like this. Great. Then you go back to this. You would start fiddling with these things and say, oh, I actually think this is gamma. Great. Poof, job done, right? That's how you should work. And that story of what I just said, your motivation, I looked at the data, it looks like this. This has to be positive. So I pick the log link function. That's the story that we want, right? Does that make sense? Yeah. And none of this there should be no problem whatsoever to use this code for fitting this. It really is those three things, the end, right? So therefore, it's all the reasoning is what we're looking for, right? And it's basically just looking at distributions of data, fitting these models, reasoning about them. Yeah, cool, very good. So I'll stop doing this. And just very quickly, you say how inference is done in this. So inference in generalized linear models is generally always done using maximum likelihood. We have this IID assumption that allows us to write up the probability of a whole data set just as a product. We do some form of gradient descent on this. For certain ones of these models, there's very tailored inference schemes. We can find loads of that. Don't bother. You don't have to bother about this. Assume it works. Yeah? Cool. So, if we now then there's this whole variety of models. I can look at the distributions. Let's look at another thing that we can play around with that we got control over. So, this matrix that we do the regression over is often referred to as a design matrix. And actually, if we do linear regression, we need in 1D, we need two, right? We need a slope and an intersection. So actually, what we're always doing when we do that we just add a constant to get the intersection, right? To get a beta 0 that doesn't depend on x. But now you can then think of, well, if I'm allowed to do that, maybe I'm allowed to do whatever other transformations that I want as well, right? So the example I had in the coursework was this. Well, let's say I'm doing regression over this. It's clearly not linear in x because it looks like this. There's a square and there's sine terms and so forth. You're always allowed to then create a design matrix that looks like this. Yeah, so you can say now each term that I'm going to do regression over, each explanatory variable, actually is a transformed version of what I have. So if I do that, I can now pick whatever this was, 3 of these, and then I can apply whatever framework I wanted afterwards on top of that. So that is creating a design matrix because you know something about this, right? Okay. So then this sounds great, right? Because let's just think of a scenario where this now would allow me to, I don't know what my explanatory variables are, so I'm going to do a for loop that creates a design matrix that includes every function that I've ever heard of, and then I'm just going to do regression over that, right? Then I'm fine, right? Great, because now it includes everything, so you can do anything, right? So let's just do that, of adding another one. So now I've just added minus sign as well to this one. Hopefully the image on the left, if I kept the random number, doesn't change. These are actually 2 different solutions to that. The image looks very similar, right? Now, if we look at the solution, so this is the beta, you can see that now it's like 0.1, 0.1, and the previous solution had 0.2 on the sign, right? So what the model, what the inference scheme now have you said, oh great, you gave me another one. I'll use that one, happy. Right? We can add more sign terms and it's going to pick more of them, right? So actually this is a bit useless, right? It doesn't actually help us because the maximum likelihood formulation, the inference schemes, will just use as many of these as it humanly can, right? So if you just expand this matrix with every known function known to man, well, you're not going to get much, right? You're just going to get this very, very over-explained thing where it's very hard to understand what these betas are. In an ideal scenario, what I would want is something that says, I add loads of these, and then I end up saying, oh, you know, I don't need that one, put the 0 there. Right, that would be great. Okay, let's take that one level more, one level even further of just madness, of saying that let's take what we usually refer to as a non-parametric explanation, and let's say that you gave me, in this case, 5 data points at x1 to 5, I think, and these are my training data points. And what I'm going to do is that I'm going to do a regression task where I put the basis function, in this case these bumps, at each data point, right? So now I'm going to have a design matrix when I'm training, which is going to be square. Because there's many functions or as many explanatory variables as I got response variables to explain, right? Well, this is super easy for the model to explain, right? Because now you've just created a lookup table for it, right? It's super, super simple. But this is a really powerful technique because what this allows you to do is to reinterpret your regression task in a different way. So what I've done here, right, is that I put one of these bumps on each data point that I've seen. If I would now, in an ideal world, learn a set of betas here, what those betas would say would be, in order to predict this, this data point in your training set is the most important one, right? And that's a really, really powerful notion, right? It gives you a different way of explaining the data, not through a function of saying, oh, it's this, like in this case, oh, most of this is explained by the sine x squared term, right? That's what having this large beta would say. In this setting, if the beta for the first bump will be much higher than the others, then you're effectively saying that training data point is much more important for explaining this function than any other training data points. That's a really powerful narrative to be able to say, right? Cool. So how do we crack that? How do we solve systems where we have way too many possible explanations? We do that by regularization. So the maximum likelihood that we did to use inference, it has no preference towards any solution. So the only thing that we optimize for is the thing that fits the data as well as possible. So we might get different results, but those are basically down to how we optimize this thing. If we got symmetrical explanations, by the way we started our gradient descent, for example, we might end up with different solutions. So what we do to crack this is that we introduce some form of regularization term. So this is a term that is added which only depends on beta. And normally what we're going to do, and what's included in the Statsmodels package, is that we include some form of norm. So we're penalizing different norms in this case. So that will be something where we can include an inductive bias on the betas that we find, right? So now we have this balance between something that depends on our data fit and something that regularizes the solution that we find. So the two ones that you'll normally see is the L1 norm, which is the red one, and the L2 norm, which is the blue one. Okay. So my hobby explanation of this, of why they do different things, you've probably seen this before, is this. So I have a function like this, and I need a certain amount of values in beta to be able to push a prediction up there. If I take the blue one, so the L2 norm, I'm penalizing the norm. So in an ideal setting, I want both of them to be 0, right? No betas whatsoever. But then I can't represent the data. So now, how do I get as much beta as possible with the blue one? Well, the blue one doesn't effectively differentiate any direction. So now I would pick a direction that picks an equal number of the betas. So put equal values on it too. While for the red one, I can get much further if I go axis aligned. If I go in the middle, then I have a massive gap between the red and the blue. So that's the notion of what the two solutions they prefer. So that's why we say the red one prefers solution that lies here or there, so on the axes, which means it pushes betas to 0 and picks as few betas as possible, while the blue one picks as many betas as possible, right? And wants them all to be of equal size, right? That's the ideal thing, because now you're on it. So this is very simple in Statsmodels. So you now have two parameters to choose. You have this term called L1 underscore WT. To pick it to be 0, that means you get L2, which is rigged regression, it's also called. So L2 regularization. If you pick it to be 1, you get L1, which is also called Lasso. And alpha is the value of the penalty, how much you take the regularizer in. So that, you change the command end of fit to end of fit regularized. And that's it. Right? Try both of them, and you'll see the different solutions that you'll get. Cool. So I'm going to wrap up this. So all the things that we went through then, so think about all the tools this has given you now then. So the first thing to think about, stare at your data, look at it, and see what response variable, how is my response variable distributed? Does this data, like, do I know anything what this data is? Oh, it doesn't make sense that someone sells houses for negative prices. Or maybe it does, it's a tax scheme or something. But you know, look at the data, look at distributions, right? That's number one, okay? Then the thing is, okay, think about the link function. This is the thing that would allow you, one, to force the values of your linear predictor into a specific range. For example, it would also give you the structure if you have something that's exponential and so forth. So think about the link function, okay? Then the design matrix. What is the features of the explanatory variables? We would much rather that you spend time thinking about this than going down the route of saying, I'm going to add everything and put the cool regularizer. Well, that's the machine learning nonsense part of it, right? The much more interesting part is if you design the design matrix and have a really good argument for why you've included something, right? Yeah, I think this is important. I think the distance to this thing in the database is really important for this thing. And I've included that. Well, awesome, right? Great. That's exactly what we want to see, right? So spend time on that. And then the last thing then would be, and I would think this is more, well, this is really the last thing, is saying, well, you might have added now, you've created this design matrix that include lots of different things. And some of them are not going to be independent, right? There's a lot of them which probably says the same thing. Cool, that's when your regularizer comes in. So rather than saying, oh, I'm going to say that this house price or this something is dependent on these three things, but it turns out if it has a balcony or if it has a, you know, a roof terrace or something, you put them both as features, actually they're both the same. That was a really bad example, but I think you get, you don't have two, right? Do you? No, but two things that actually means the same thing, right? Now you can put, for example, a Lasso regularizer, and it would say, you know what? I don't need to use both of these. Actually, one of them is sufficient to explain this data. That tells a story again, right? That zero beta is going to tell a really important story. You can do that regression with both of them and say, oh, actually, if I remove this one was needed again. Ah, possibly they correlate or so forth. You could do a correlation plot, right? So think about these things. So then some more thoughts. Can you split up the data using some criteria, right? Rather than you saying, oh, I'm going to take all of this data for everything, and I'm just going to fit the perfect model for that. You're probably making your life a lot harder than it needs to be, right? Find a criterion that you can split the data up by and fit it according to that, right? Much, much more sensible to do in many cases. So that would be building effectively a localized model. So another thing would be, well, instead of finding the perfect model to this, fit one model, remove the effect from that model, and fit another model to the residual that you have, right? Sounds like a very sensible thing to do. So think about that. So the notion, again, you are not going to be able to, and that's not your task either, to find this perfect model. But what you should have is an argument for why you use a specific model. And that argument should not be, well, this is the one that fits best to the data. No, I could do that myself. I'll write a for loop and I'll check the log likelihood and I'll pick the best one. No, we want an argument that says, I did this because of that, this, that, and this, and that's the model I picked. That's interesting. That's an argument that you can tell someone that you're a user of this model. If you're actually fitting this for making a decision, you're going to feed this information to a decision maker. They're not going to be interested in log likelihoods. They're going to be interested in your argument for why you picked it. Cool. And with that, I'm going to end. I'm going to stop the recording. And if you've got any questions, then feel free.
If anyone here having trouble, you should all be able to access MariaDB.